Invisible forces shape every galaxy, yet we can't see them. Today we unveil 10 dark matter enigmas that defy explanation, and number 1 is something almost nobody guesses, so stay until the end. Mysterious patterns in the cosmic microwave background first hinted that something unseen was tugging at the universe's earliest light. In the early 1990s, researchers spotted a cold spot, an area slightly cooler than its surroundings, sparking debates about whether it was a statistical fluke or a sign of a massive void lined with dark matter. Subsequent analyses using the Planck satellite suggested the anomaly could be a lensing effect from a supercluster of dark matter, invisible yet massive enough to warp microwave photons. If true, this would be one of the earliest indirect fingerprints of dark matter, showing how its gravity can shape radiation billions of years old. The story reminds us that even the faintest whispers in the sky can echo the universe's hidden architecture, urging scientists to keep listening for more subtle clues.
Hidden within the faint glow of the dwarf galaxy NGC 1052DF2 lies a halo that challenges conventional dark matter expectations. Discovered in 2018, this galaxy appears to contain far less dark matter than similar systems, prompting astronomers to wonder whether we are witnessing a stripped halo or a genuine anomaly. Follow-up observations with the Hubble Space Telescope measured the motions of its globular clusters, finding velocities too low to require the usual dark matter mass. Some theories propose that tidal interactions with a nearby massive galaxy ripped away the halo, while others suggest exotic physics like modified gravity. This ghostly case forces researchers to rethink how dark matter assembles around small galaxies, illustrating that the cosmic scaffolding can sometimes be surprisingly fragile.
Surprisingly, a burst of radio waves in April 2022, catalogued as FRB 20201124A, revealed repeating patterns that hinted at an unseen dark matter influence. Fast radio bursts are brief, intense flashes whose origins remain elusive, but this particular source displayed periodic activity every 16.35 days. Some scientists propose that a rotating dark matter clump, perhaps a dense Axion star, could be modulating the burst's emission as it orbits a magnetar. While alternative explanations involve binary companions or plasma lensing, the dark matter hypothesis sparked a wave of theoretical papers exploring how compact dark objects might interact with electromagnetic phenomena. If verified, this would be the first time dark matter directly modulates a detectable astrophysical signal, opening a novel window into the invisible sector of the cosmos.
Imagine two galaxy clusters crashing at thousands of kilometers per second, their galaxies passing through like ghosts while a massive, invisible component drags behind. The Bullet cluster, observed in 2006, offers exactly that spectacle, an X-ray bright shock front separating ordinary gas from a region of gravitational lensing that aligns with the collision's trajectory. This separation provides compelling, though not absolute, evidence that most of the mass is non-luminous dark matter. Researchers used the lensing map to infer an unseen mass roughly 10 times greater than the visible matter, reinforcing the particle dark matter paradigm. Yet some still debate whether modified gravity could reproduce the lensing pattern. Regardless, the Bullet cluster remains a cornerstone case where dark matter's gravitational pull is visualized as a ghostly weight trailing a cosmic collision.
Scientists have long relied on galaxy rotation curves to infer dark matter halos, and the flatness of these curves remains a puzzling hallmark. In the early 1970s, Vera Rubin's measurements of spiral galaxies showed that stars far from the center orbit at speeds that should have caused them to fly apart if only visible matter were present. This discrepancy suggested an extended halo of unseen mass. Modern surveys using radio telescopes to map hydrogen gas confirm that rotation curves stay flat out to the galaxy's edge, reinforcing the dark matter model. However, recent high-resolution simulations hint that baryonic feedback, stellar winds and supernovae might mimic some of the effect. The ongoing debate highlights how a single observational clue can fuel decades of theoretical development.
In 2024, a massive galaxy cluster named CLJ10013220 unveiled a spectacular Einstein ring that revealed a dark matter distribution unlike any seen before. The ring's distortion pattern, captured by the James Webb Space Telescope, indicated a dense core of dark matter offset from the luminous galaxies, suggesting a possible subhalo collision within the larger cluster. Researchers modeled the lensing effect, finding that the dark matter appears clumped in pockets, perhaps hinting at self-interacting dark matter particles that can scatter off each other. While alternative explanations involve projection effects, the observation fuels speculation that dark matter may possess richer internal dynamics than a simple cold, collisionless fluid. This lensing portrait underscores how gravity can act as a cosmic microscope, exposing the hidden architecture of the universe.
Few people know that the Milky Way should host hundreds of tiny satellite galaxies, yet only a few dozen have been observed, a discrepancy called the missing satellite problem. Simulations predict many low-mass dark matter halos that never formed stars, making them virtually invisible. Recent deep sky surveys using the Vera C. Rubin Observatory have begun to uncover ultrafaint dwarfs, but the count still falls short of theoretical expectations. Some explanations invoke warm dark matter, which would suppress the formation of small halos, while others suggest that reionization stripped gas from nascent dwarfs, preventing star formation. This ongoing mystery illustrates how the scarcity of observable dwarf galaxies challenges our understanding of dark matter's particle properties and its role in galaxy formation.
Deep within the cosmic web lies an immense region, almost entirely empty of galaxies, known as the Great Void. Spanning roughly 1 billion light-years across, this underdensity offers a unique laboratory for testing dark matter models. If dark matter clusters uniformly, even voids should contain a faint background of particles, influencing the motion of surrounding galaxies through subtle gravitational pull. Observations of galaxy velocities at the void's edge suggest a lower-than-expected dark matter density, prompting some researchers to propose that dark matter might be less clumpy on the largest scales. Others argue that observational biases or cosmic variance could explain the discrepancy. Either way, the deep void forces cosmologists to examine whether the universe's largest empty spaces hide unexpected dark matter behavior.
Unexpectedly, a series of underground experiments in 2025 reported excess X-ray emission around 3.5 keV, a signal some interpret as the decay of sterile neutrinos, a hypothetical dark matter particle. While the detection remains controversial, the signal appears in multiple galaxy clusters.
Finally, the 21-centimeter hydrogen line is becoming the next frontier for mapping dark matter across cosmic time. By measuring the faint radio emission from neutral hydrogen gas, astronomers can trace the large-scale structure of the universe, indirectly revealing where dark matter resides. The Hydrogen Epoch of Reionization Array, HERA, and the upcoming Square Kilometre Array aim to produce three-dimensional maps of hydrogen distribution from the universe's first billion years. Early results already show subtle fluctuations that align with dark matter simulations, offering a promising route to test competing theories, including self-interacting or fuzzy dark matter. As these surveys mature, they could finally provide a direct, statistical portrait of the invisible scaffolding that shapes every galaxy, completing our journey through the most mysterious dark matter objects known today.
We've traveled from the faint whisper of the cosmic background to the bold promise of 21-centimeter maps, uncovering how each mystery deepens our wonder about the unseen universe. If you enjoyed this voyage through dark matter's most puzzling objects, subscribe so you won't miss the next mind-blowing list, new discoveries every week. Which revelation left you the most awestruck? Share your thoughts below, and give this video a like if it sparked your curiosity.